Hey everyone, welcome back to my channel. Today we're diving deep into PyTorch, one of the most popular deep learning frameworks used by researchers and industry professionals worldwide. PyTorch was developed by Facebook's AI Research Lab and has become the go-to framework for deep learning research. What makes PyTorch special? It's dynamic, intuitive, and provides excellent debugging capabilities with its eager execution model. Think of it as Python for deep learning. It feels natural and Pythonic. Now, you might be wondering, how does PyTorch compare to TensorFlow? Unlike TensorFlow's static computational graphs, PyTorch uses dynamic computational graphs, which means you can modify your network architecture on the fly during runtime. This makes it incredibly flexible for research and experimentation. It's like the difference between writing a script versus compiling a program. Today, we'll cover everything from basic tensor operations to building complex neural networks, GPU acceleration, and even transfer learning. By the end of this tutorial, you'll have a solid foundation to start your own PyTorch projects. So grab your favorite beverage and let's get started. Let's start with installation. The easiest way is using pip or conda. Head over to pytorch.org and use their installation selector. This website is fantastic because it automatically generates the right installation command based on your operating system, Python version, and whether you want CPU or GPU support. As you can see here, I'm selecting my configuration. I'll choose Stable Build, my operating system, pip package manager, Python, and let's say I want CUDA support. Notice how the command updates automatically. For CPU-only installation, simply run pip install torch, torch vision, and torch audio. This command installs 3 packages. Torch is the core PyTorch library. Torch vision provides computer vision utilities and pre-trained models. And torch audio handles audio processing tasks. For GPU support with CUDA, you'll need pip install torch, torch vision, and torch audio, --index URL, https://download.pytorch.org/whl/cu118. Notice the additional index URL. This tells pip to download the CUDA-enabled version. The CU118 indicates CUDA 118 compatibility. Make sure this matches your CUDA driver version. Let's verify our installation works correctly. The first line imports PyTorch. If this runs without error, the installation worked. The second line prints the version number, which helps with troubleshooting. The third line is crucial. It tells us if GPU acceleration is available. If you installed the CUDA version and have a compatible GPU, this should return true. Now, let's talk about tensors, the fundamental building blocks of PyTorch. Think of tensors as multidimensional arrays similar to NumPy arrays, but with GPU acceleration capabilities. A scalar is a zero-dimensional tensor, a vector is one-dimensional, a matrix is two-dimensional, and we can go higher. Creating tensors is straightforward. Let me show you several ways. Here, I'm creating a 2x3 tensor by passing a nested list. The outer list represents rows, inner lists represent columns. This is the most explicit way to create tensors. Data types matter in deep learning for memory efficiency and numerical precision. By default, PyTorch infers the type, but you can specify it explicitly. Float32 is most common for neural networks. These factory functions are incredibly useful. Zeros creates a tensor filled with zeros, great for initializing weights or creating masks. Ones creates a tensor of ones. RNN creates a tensor with random numbers from a normal distribution. This is often used for weight initialization. Every tensor has important properties you need to understand. The shape tells us the dimensions. Here we have a 3D tensor with dimensions 3, 4, and 5. The D-type shows the data type. Float32 is default for RNN. The device tells us where the tensor is stored. CPU by default, but it could be on GPU. This becomes crucial when we start using GPU acceleration.
Tensor indexing works just like NumPy, but let me walk through the most important patterns. This accesses the element at row 0, column 1, which is 2. Remember, indexing is zero-based. This slice selects from row 1 to the end, that's what 1 colon means, and columns 0 and 1, that's what colon 2 means. Slicing is incredibly powerful for extracting portions of data. Negative indexing works too. -1 means the last element. This gives us the entire last column. Reshaping is crucial for neural networks because different layers expect different input shapes. Here I'm taking a 1D tensor with 12 elements and reshaping it to 3 rows and 4 columns. The total number of elements must stay the same. 12 equals 3 times 4. The -1 is a powerful feature. It tells PyTorch to calculate this dimension automatically. Since we have 12 elements total, -1 becomes 12, giving us a flat vector. Unsqueeze adds a dimension of size 1. This is often needed when you have a single sample, but the model expects a batch. Squeeze removes dimensions of size 1. These operations are essential for matching tensor shapes between different parts of your model. PyTorch provides extensive mathematical operations. Let's explore the most important ones. These are element-wise operations. They operate on corresponding elements. So 1 plus 4 equals 5, 2 plus 5 equals 7, 3 plus 6 equals 9 for addition. Element-wise multiplication gives us 14 equals 4, 2, 5 equals 10, 3 times 6 equals 18. These operations are the building blocks of neural network computations. Matrix multiplication is fundamental in neural networks. Notice the dimensions. We can multiply a 3x4 matrix with a 4x2 matrix because the inner dimensions match. 4. The result is 3x2. This is how data flows through neural network layers. Aggregation functions are essential for data analysis and loss calculations. The mean gives us the average of all elements, useful for normalization. When we specify dim equals 0, we're summing along the first dimension, rows, giving us column sums. Dim equals 1 operates along columns, giving us row statistics. Argmax returns the index of the maximum value, not the value itself. This is crucial for classification tasks where we need to find which class has the highest probability. One of PyTorch's biggest advantages is seamless GPU acceleration. Modern GPUs have thousands of cores optimized for parallel computation, making them perfect for the matrix operations in deep learning. This creates a device object that automatically selects GPU if available, otherwise falls back to CPU. This pattern makes your code portable between different machines. There are 2 ways to get tensors on GPU. Either create on CPU and move them, or create directly on GPU. The .to method is flexible and works with any device. Creating directly on GPU is more efficient if you don't need the CPU version. Let's see the dramatic performance difference. The synchronized call is important. GPU operations are asynchronous, so we need to wait for completion to get accurate timing. Typical speedups range from 10x to 100x, depending on the operation and hardware. This is why GPU acceleration is essential for training large models. Now let's build our first neural network using the torch.nn module. We'll create a simple feed-forward network for image classification. All PyTorch models inherit from nn.module. The init method defines our layers. nn.linear creates fully connected layers. The first parameter is input features, the second is output features. Dropout helps prevent overfitting by randomly setting some neurons to 0 during training. The forward method defines how data flows through the network. We apply ReLU activation after each hidden layer. This introduces nonlinearity, allowing the network to learn complex patterns. Notice we don't apply activation to the final layer. That's handled by the loss function. Here we create a model for RNNs digit recognition, 784 input features, 28 by 28 pixels, 128 hidden units, and 10 output classes, digits 0 to 9. Printing the model shows its architecture. For training, we need 3 key components: model, loss function, and optimizer. Cross-entropy loss is perfect for multi-class classification. It combines softmax and negative log likelihood. Atom optimizer is generally the best starting point. It adapts the learning rate automatically. Learning rate 0.001 is a good default. Don't forget to move your model to GPU.
Here's the standard training loop structure in PyTorch. Let me break this down step by step. Model.train sets the model to training mode. This affects dropout and batch normalization. We loop through epochs, complete passes through the dataset, then through batches within each epoch. The zero-grad call is crucial. PyTorch accumulates gradients, so we need to clear them each iteration. The forward pass computes predictions, then we calculate loss. Loss.backward computes gradients using automatic differentiation, and optimizer.step updates the weights. We track statistics for monitoring training progress. Torch.max returns both values and indices. We only need indices, predictions. We accumulate correct predictions and calculate accuracy as a percentage. And here's how we evaluate our model. Model.eval sets evaluation mode. This turns off dropout and batch normalization updates. Torch.nograd is crucial for testing. It disables gradient computation, saving memory and speeding up inference. The rest is similar to training but without backpropagation. PyTorch provides powerful tools for data handling. Let's explore datasets and data loaders. Transforms are pre-processing steps applied to data. Tensor converts PIL images or NumPy arrays to PyTorch tensors and scales pixel values from 0 to 255 to 0 to 1. Normalize standardizes the data. Here we're centering around 0.5 with standard deviation 0.5, effectively scaling to -1 to 1 range. MNITS is a built-in dataset in Torch Vision. Setting download equals true automatically downloads the dataset if it doesn't exist. The transform parameter applies our pre-processing pipeline to each sample. Data loaders handle batching and shuffling. Data loader wraps a dataset and provides batching, shuffling, and parallel loading. Batch size equals 64 means we process 64 samples at once. This balances memory usage and gradient quality. Shuffle equals true randomizes sample order, which helps training. NumWorkers equals 2 uses 2 processes for parallel data loading, speeding up training. This shows us the actual tensor shapes we'll work with. For MNIST, images will be 64, 1, 28 by 28, batch size 64, 1 channel, grayscale, and 28 by 28 pixels. Labels will be 64, 1 label per image. You can also create custom datasets for your own data. Custom datasets must implement 3 methods. Init stores your data, len returns the dataset size, and getItem returns a single sample. This pattern works with any data format: images, text, audio, or tabular data. Data augmentation helps improve model generalization by artificially expanding your dataset with transform versions of your original data. Each transform adds variation to your data. Random rotation rotates images up to 10 degrees. This helps the model handle rotated objects. Random horizontal flip mirrors images with 50% probability. Random resized crop crops and resizes to introduce scale variation. Color jitter varies brightness and contrast, making the model more robust to lighting changes. Now, each time we load a sample, it gets a different random transformation. This effectively multiplies our data size and helps prevent overfitting. Efficient batch processing is crucial for performance. This function encapsulates batch processing logic. Always move data to the correct device first. Processing batches instead of individual samples is much more efficient because it leverages vectorized operations. Let's build more advanced models. Here's a convolutional neural network for image recognition. CNNs are designed for image data. Conv 2D layers detect features using learnable filters. The first parameter is input channels, 1 for grayscale. Second is output channels, number of filters. Kernel.size is the filter size. Padding equals 1 keeps the spatial dimensions the same. MaxPool2D reduces spatial dimensions by taking the maximum value in 2x2 regions. This reduces computation and provides translation invariance. The final calculation, 128 times 3 times 3, comes from tracking how the spatial dimensions shrink through the network. The forward pass shows how spatial dimensions shrink. Each conv-ReLU-pool combination halves the spatial size while increasing the number of features. The view operation flattens the 2D feature maps into a 1D vector for the fully connected layers. Here's a recurrent neural network for sequence processing. RNNs process sequences by maintaining hidden state across time steps. LSTM is a type of RNN that handles long sequences better than vanilla RNNs. We initialize hidden states with zeros for each batch. The LSTM returns outputs for all time steps, but for classification, we typically only use the last output. Transfer learning lets us leverage pre-trained models for new tasks. Instead of training from scratch, we start with the model trained on a large dataset like ImageNet. Setting pre-trained equals true loads weights trained on ImageNet. Freezing parameters with requires grad equals false prevents them from updating during training. We only replace the final classification layer to match our number of classes. This approach is fast and often gives better results than training from scratch. For fine-tuning, we can unfreeze some layers. Fine-tuning updates more layers but with different learning rates. Earlier layers learned general features, so we update them slowly, 1E-4. The final layer is task-specific, so we use a higher learning rate, 1E-3. This balances preserving learned features with adapting to new tasks. Here's a complete transfer learning example. MobileNet v2 is optimized for mobile devices, but works great for transfer learning. The classifier attribute contains the final layers. This pattern works with any pre-trained model. Just identify and replace the final classification layers. Congratulations! You've learned the fundamentals of PyTorch. Let's recap what we covered today. PyTorch installation and setup. We learned how to install PyTorch with CPU or GPU support. Tensor operations and GPU acceleration, the foundation of all PyTorch computations. Building neural networks with NN.module, creating custom architectures. Training and testing procedures, the complete machine learning workflow. Data handling with data loaders, efficient data processing pipelines. Advanced models, CNN, RNN, specialized architectures for different data types. Transfer learning techniques, leveraging pre-trained models for faster development. Here are your next steps to master PyTorch. 1. Practice projects. Build image classifiers, text analyzers, or recommendation systems. Start with simple datasets like CFAR10 or IMDb reviews. 2. Explore advanced topics. Dive into GANs for generating new data, transformers for natural language processing, or reinforcement learning for game AI. 3. Join the community. Engage with PyTorch forums, contribute to GitHub projects, and read research papers to stay current. 4. Stay updated. Follow PyTorch releases and new features. The framework is constantly evolving with new optimizations and capabilities.
Useful resources for your PyTorch journey. Official PyTorch documentation, pytorch.org, the most comprehensive and up-to-date reference. PyTorch tutorials and examples on GitHub, real implementations you can learn from. Papers with code. Find implementations of cutting-edge research papers. Fast.ai courses, practical deep learning with excellent PyTorch examples. PyTorch Lightning, a higher-level framework that reduces boilerplate code. That's a wrap on our comprehensive PyTorch tutorial. You now have the foundation to build your own deep learning projects. Remember, the key to mastering PyTorch is practice. Start with simple projects and gradually increase complexity. If you found this helpful, please like and subscribe for more machine learning content. Your support helps me create more detailed tutorials like this one.